Hi guys, in today's video I would like to show you how I made my own STM32 bootloader for this board. And basically this bootloader is capable of modifying and jumping to two different applications. And it uses USB peripheral to update those applications. So once you will understand how this all works, you will be able to make your own bootloader on your own. So those who don't know what a bootloader is, it is basically an application that sits at the beginning of the memory, of the flash memory, and this application is capable of erasing other parts of the memory and putting there new data, such as new application, which is many times called a firmware. So basically, this application is supposed to be there forever, and via this application you will be able to update your application or firmware for your own product. Basically, this bootloader is basically an application that is supposed to be there forever, and the client, as he will buy, for example, your product, he will be able to update his applications with new features, bug fixes, etc. So as you can see, this STM32 board has 64 kilobytes of flash memory in total. So basically I have split this flash memory into three separate partitions. And basically the first partition has 20 kilobytes for the bootloader, and right after that there are two other partitions for two applications, and each one of them has 22 kilobytes. And later in this video I will explain you what you should modify and how you should set up your projects in order to have proper flash memory origin and proper size. This is mainly for the vector table and for the linker. So basically this STM32 board uses USB peripheral, which is initialized as virtual COM port, and it is used for the flash mode to upload new firmware to your flash memory. And basically this boot 1 pin is used to select either jump mode or flash mode at the booting up or resetting the MCU. And basically this boot 1 pin is simply an ordinary PB2 GPIO input pin. And to select which one application you would like to flash or to jump to, you just need to use this simple switch that sets the PB11 to logical 1 or 0. And over here you can see these 22 ohm resistors, which are for the USB data plus and data minus. And this 1.5K resistor is used to enable and disable or connect or disconnect the USB peripheral from the computer. So this way your computer knows when your USB device has connected or disconnected. And as I explained just a few moments ago, this simple switch is used for the bootloader to select your application 1 or application 2. And this middle pin isn't connected directly here, but it is connected over here to PB11, and it is used to select the logical 0 or logical 1. So that's simply all for this introduction, and now I'm going to demonstrate these applications, what they do. So now I'm holding this reset button, and after releasing this, the bootloader is gonna read this boot 1 pin that says it is time for a jump, and this switch tells the bootloader to jump to application 1. and after I release it, the bootloader already jumped to application 1 and it just blinks. That's this application 1, and on this position we are still in the application 1 because the bootloader is already gone. It jumped out of the bootloader to this application 1, and simply I'm using this switch to read the state, and it is a part of this application 1. So this is the application 1, and I'm gonna keep this switch in this position, and after resetting this microcontroller, it's gonna jump to application 2. So now it's in application 2 and this LED is on, and it has 1 second delay after toggling this switch. So this is a simple application 2, but the point is that this microcontroller is running currently application 2, and the bootloader was running only at the very beginning after the reset. So basically after it jumps out of its boundaries, it runs a totally different application. So this is basically the point of the bootloader, of this example, that it can jump to multiple different applications, as many as you want. So now I have switched this boot 1 pin to the flash mode, and after releasing reset pin, the LED is gonna blink 10 times quite rapidly, and afterwards it's gonna initialize as a virtual COM port. So now it has initialized as a virtual COM port, and I've also made this STM32 Flasher application. Let me show you. So this is a Java application that is capable of erasing the flash memory and flashing new firmware. So let me just select this bootloader and connect to it, and now I can erase the flash memory. So now it is erased, and after I disconnect from this, I can close this, and after I set this boot 1 pin to 0 again to jump mode, after I reset this microcontroller, basically it's not gonna find any application, and this LED is gonna blink as SOS signal. So 3 short blinks, 3 long, and 3 short. So I'm holding the reset. So 3 short, 3 long blinks, and 3 short. So it's signalizing that there is a problem. In this case, the application 1 is missing. So in the next cut, I'm gonna show you that you can flash there again a new application. So I'm back again. So basically I've switched this to the flash mode, and we are still in this error mode. And after I reset this microcontroller, it's gonna blink 10 times. So now we are back initialized, and I can run this application again, and I can connect to this bootloader, and now I can go to this file chooser and pick up this application 1. But for now I can show you what happens if you pick up a quite big file. As you remember, this memory has only 22 kilobytes of size. So when you pick up a lot bigger file, such as 68 kilobytes, it's gonna show you this error message, which says that this memory is really big, like 3 times bigger than it should. So this application is gonna quit. So when I connect again, I can pick up the correct file, this application 1, and now I can flash this application, and it was quite quick and it's done. So now I can disconnect from this and close this application. So this is how simply a user can update his own application. So now I can switch back to this jump mode and reset this microcontroller. And as you can see, this LED blinks as it was before, and now it's gonna blink faster. So this is the simple application 1. So let's start explaining how you can make your own bootloader. Basically, you need to keep the origin of the flash as it is, but to determine the size of your bootloader, you need to write your code and have it almost finished. And after you build your almost finished application, you will be able to estimate the size of the flash memory it will take. So in my case, I ended up having 19.5 kilobytes of flash memory, and one sector or one page of this STM32 flash memory has 1 kilobyte. And your next application can start right after your bootloader's last page. So basically, this bootloader takes 20 kilobytes of flash memory, therefore 20 pages. And on the 21st page, your next application can start. So therefore, I've ended up having this 19.5 kilobytes of flash memory, and I had to round it up to those 20 pages, which is 20 kilobytes, and it is 20,480 bytes. And I've used this calculator to check the size of the memory. It converts the kilobytes to decimal values. And basically, therefore, I knew that the next application can start with this 5,000 hexadecimal offset. And to find out how big your page size is in your particular model, you need to go, for example, to a reference manual where you can find it out. They are quite long, like over 1,000 pages long, but you will find basically everything there you need. So when it comes to a bootloader project, you need to modify basically more or less only this flash, this linker called flash LD, and you need to keep the origin, but you need to lower the size according to your bootloader application size. And it should be rounded up to your page. So when it takes 19.5 kilobytes, for example, you need to round it up to 20 kilobytes. And over here, I have put there just a few definitions from the code, just to get around. So I've decided to define where the application 1 starts and application 2 starts. And over here you have explained that you have this origin plus bootloader size. It's the origin of the application 1. And application 2 starts as the origin of the flash memory plus bootloader size plus the allocated application 1 size, which is 22 kilobytes. So therefore I was able to define how much memory I would like to allocate for each flash memory partition, and each page size for this on this STM32 board has 1 kilobyte. So therefore I know how many pages I need to erase before I flash a new firmware there. And here are just a few definitions. This is for the jump. It contains stack pointer and program counter value, and basically once you set up this value, like where to jump, it's just you just need to de-initialize everything, and then you can use this assembly command to jump to your new application. But you need to properly de-initialize your microcontroller, and to do it properly you just need to do it the opposite way as you initialized your microcontroller. So basically, when you first initialize the hole in it, then system clock, and then your GPIOs and other peripherals, you should do it the opposite way. That's the safest way to do it. Because when you forget to de-initialize something, for example PWM, and you will jump to your next application, the PWM will be still running, or any peripheral that you will keep initialized. So when you, for example, initialize the SPI and you forget to de-initialize it, it's gonna be still configured as it was in your bootloader. So this is a really important thing to do. So when it comes to this STM32 project, I'm gonna explain it right now. So let's start with this flash.ld linker file. Basically I kept the origin and set the file size to 20 kilobytes after I knew how much memory it's gonna take. And over here I've defined a few structures. For example, for the bootloader mode, jump mode or flash mode, or to which application I would like to jump, and the status of the memory, whether it is unerased, erased, unlocked or locked. And I've also defined this application pointer, sort of. And over here's the definition of the structure that can jump to your specific application, which consists of stack pointer and the program counter, and that's basically it. So when this application starts, it just calls this bootloader init function, and I've only included this bootloader.h file. So for the main file I've just placed here this line and this line, quite simple. And when that bootloader init function is called, it just sets the flash status to unerased. I check whether the boot 1 pin is set or reset. So when it is set, it's for the flash mode, and when it is reset, it's for the jump mode. And in the flash mode, I basically blink the LED 10 times, and then I set up the USB enable pin that enables the virtual comport communication with the computer, and therefore I'm able to flash a new firmware to this microcontroller. Otherwise I turn the USB pin to 0, which disables this USB communication. And Then I read the switch and decide whether to flash or jump to application 1 or application 2. So when the mode is set up to jump mode, I just jump to application 1 or to application 2. And before that, before the jump, I read the first 10 values of the flash memory, and if it is erased, I can detect it, and I can decide to show the error blinky LED that blinks SOS signal. And if it is occupied or if there are any data, then I can jump to the function, to the new application. So that's basically it when it comes to this bootloader init function. But when this bootloader is initialized, then I use this USB peripheral and I just try to receive some commands. And this bootloader knows a few commands, for example, erase memory, flash start, that unlocks the memory and potentially erases it, and this flash finish locks the memory. And in case it receives this flash abort, it basically stops the flashing, erases the memory, and locks the memory. So it's quite straightforward. So this function waits for the commands to be received, and when the received message has length of 4 bytes, it assumes that these are data for the flashing. So basically I just try to get those data and write them to flash memory, but only in case if the status of the memory is unlocked, and in case the length of the message is different, I just jump to this message handler, which is down here in the bootloader C, and I just check what kind of command it was. So I can, as I told you, I can erase the memory, then I send back the message, the report that the flash memory was erased, or I can I can start the flash mode that unlocks and erases the memory. So here are all the functions up here. Or I can finish the flashing or abort. And if there's some kind of problem, or I just receive the messages, those commands in incorrect steps, I just report back that that's an error. So that's basically it. When it comes to this erase memory, I just try to unlock the flash, unlock the option bytes. Then I check like which application was selected. Based on this application, I just can set up the origin of the address, and then based on the flash bank size or partition of the flash memory divided by the page size, I know how many pages I should erase. And then I erase the memory and then lock the memory back and also lock the option bytes. And then I just set flash status to erased. So that's basically it. And when it comes to unlock and flash memory, I just do the same. I just unlock the flash memory, unlock the option bytes. Then if the memory has not been erased, I should just erase it again, and then I just keep the memory unlocked. And if it was erased in previous step, then I don't have to erase the memory because it was already erased. And when it comes to lock the flash memory, this is supposed to be called after flashing new firmware. Then I just call these two commands to lock the flash, and this function to lock the option bytes. And when it comes to this abort, I just call these two functions to lock the flash and erase the memory. So that's basically it. And when I try to flash the memory, I should go back to this function. So when I receive the 4 bytes, I suppose that those are for the flash memory, and I just basically increment the address. It's over here, this flash offset. So when I successfully write the word, I just increment this offset by 4 bytes, because this is 32-bit microcontroller, which means that I can receive 4 bytes at once and write them down. So this means that before I flash this application, I have to check which application is already selected. Therefore, I know where I should write those data, and afterwards I just verify by reading that those data, if they were correctly written or not. So if everything was successfully written, then I increment the offset, and then return back to this USB function. So basically, afterwards it was successfully written. I just sent back this report that flashing was okay of that particular word, which is 4 bytes. So I need to unlock the memory, write the new firmware, and then lock the memory. So that's basically it. It's not that complicated. You can follow my README file over here. So that should explain how to achieve it. You just need to know that you need to first unlock the memory. It should be erased, and then you can write new data and lock the memory again. So that's all for this STM32 bootloader. So when I move back, I can now start explaining how you can set up your application 1 and application 2, because this setup differs. So let's move on to this application 1. Okay, so let's have a look at this application 1. Basically, over here I have changed the offset of this application 1 by 5000 in hexadecimal, and I've also defined this flash size to be 22 kilobytes. It is the size of this partition. So basically, for the application 1, which is written over here, you just need to change the linker to have a specific origin offset and the specific length. And when it comes to the C code, you just need to go and go to this system STM32.c and look for this vector table offset. And you need to uncomment one definition, this user vector table address, and then you can set up your offset. So let's go on and search this. So when I go over here and press Ctrl H, I can go to this file search and search it, and it found this result. So basically this line was commented originally. I've uncommented it, and then I was able to set up this offset to 5000 hexadecimal, which is 20 kilobyte offset, which is based on my bootloader size. So you should start your next application as on next page as your bootloader was taking. So when your bootloader takes, for example, 19.5 kilobytes, therefore you should round it up to your page size, so to 20 kilobytes, and then your application can start at 20 kilobytes. So that's basically it, and this program is quite simple. As you can see, I just toggle the LED pin, and I just read this switch, and if it is in logical state 1, it waits short time, and if it's in logical state 0, it waits slightly longer. So that's the difference between the short blinking and the fast blinking of the LED. So that's basically this. So this is the short, this is the long blinking, and this is the quick blinking. So this is this application 1. So it's not that complicated to make your own application with offset. You just need to set up this vector table offset by uncommenting this line and setting up this offset, and also by changing this one particular line in your linker file. And I've left here this comment, which is the shortest manual how to set it up. So that's basically it, and the same works for this application too. So it's quite similar. I've also defined this new offset, which is the offset of the bootloader and the next application. So that's the new offset, and the partition size is the same. It's 22 kilobytes. And you also have to do the same exact step as I explained you, just to look for this definition, define vector table offset, just pressing this Ctrl H again, searching it, and it's the same. I just uncommented this line, set up the new vector table offset, which should be the same as here. So if you forget to set up this offset, or if you mess something up, your interrupts will get stuck. So this is really important, that you need to have your vector table offset has to match with your linker, because, for example, such as this whole delay or any interrupt caused by, for example, UART or SPI peripheral or anything, will cause the crash of your application, so your MCU will stop. So that's a really important note here. So when I reset this board, I just jump to this application too. So this is the LED switching with 1 second delay. So that's quite simple, and that's basically all for this STM32 tutorial part. And now I can move on to this STM32 Flasher application. So basically this application contains only 4 classes. This one main class is for the graphical user interface that defines the fixed size of this stage and displays the icon and disables the resize capability of this stage, and also it initializes the comport menu and the rest of the layout. So this serial comport class tries to look for the available comport devices. It displays them, and also it contains the button to connect and to disconnect to the virtual comport, as well as these functions that contains listeners. And in case this serial comport receives this error message, for example, it calls this custom prompt, which is also available in this main class. And this class contains all the objects and variables, and over here this app functions contains all the functions of this application. Basically over here I just set up all the buttons, what they should do, like what should happen after you click on for example on button file, and what should happen afterwards. Then all the objects are set up, like labels and progress bars, etc. And I also have these other buttons to erase the memory. Like after clicking, it sends this command, and this is file chooser that tries to filter all the files visible only down to binary files. So that's quite simple. And basically this timeline tries to update the graphical user interface mainly for the progress bar as the flashing progresses. So that's basically it. And as you can see, here are just a few more functions. So this Java application is quite simple, and also when a message is received and it is complete, then basically this class calls this message handler function, which is over here. And if it receives this message that flash was erased, it sets the buttons back to its original condition as they are supposed to be. Also, when the flash is unlocked, it knows that it can start flashing the data, basically. Or if it receives the message that the flash was okay, like the flashing of one word. So this way I can increment the content of the file and send it word by word into the MCU. And this content of this file is basically this binary content, which is defined as a byte array. But it was opened after clicking this button file. So by opening that file chooser, which is basically this one, I can show it to you. After clicking this button file, which is this one, it opens this dialog window, and this file chooser window basically can filter all the binary files only, and when you open one of them, it does all these steps, such as to recalculate how much memory does it take, and all the content of the file is copied into this binary file content. So therefore all the file is read at once, and it is stored in this array, and then when the microcontroller wants to get a new data, this message handler sends a new data to it. So that's basically it, and that's all for today's tutorial, which is available on my GitHub. So when you read this closely, you should be able to make your own bootloader application. As I mentioned at the very beginning of this tutorial, if you will understand how this all works, you can make your own application. The new applications can be updated via Wi-Fi, via Bluetooth, in any way, from where you can get a new firmware binary file. So it's up to you. And if you want to try out this application, you can follow all these steps, like how to properly flash a new firmware to your STM32 board after you export or generate your own binary file that matches the vector table. So keep in mind that your vector table and your linker file have to match, otherwise any interrupt will cause the failure of the microcontroller, so the program is going to be stuck somewhere. So keep this in mind. Just try to understand it, not to copy paste my code. Just try to learn from this, and that's all. So keep trying, keep learning. Thanks for watching. See you next time. Bye.